In this video, we are going to talk about the integration of the equation of motions in molecular dynamics. What do we mean with integration? Let's say that we have calculated the force acting on each atom using the force field that we defined in another video. Now we want to obtain the trajectory followed by these atoms subject to these forces. In order to do that, we have to solve the Newton equation of motion, which is represented here. So given the force, we have to integrate in time the position of the particle, and we will obtain the trajectory. The problem is that we have so many atoms in our system, so many particles. Just remember that a typical MD simulations uses tens of thousands of atoms, and the functional form of the force field is so complicated that we cannot solve this equation analytically. We have to use numerical integration. The most used numerical integrating algorithm in molecular dynamics is called the Verlet algorithm, from the guy that invented it in the 70s. Basically, you are assuming that the position, velocities, and acceleration can be approximated by a Taylor series expansion. So you write the Taylor series expansion for the position occupied by an atom at time t plus delta t. That means in the future, the position that was occupied by this atom at time t minus delta t. That means in the past. If you sum these two equations, you obtain this formulation here. So with this equation, knowing the position of the atom at time t minus delta t and the position of the atoms at the time t and the total force acting on the atom at time t, we can calculate the force at the time t plus delta t. Now the position of the atom at time t plus delta t becomes our new present, and we can calculate again, knowing the position in the past and the present, the position of the atom in another step in the future. By doing this thousands, hundreds of thousands, or millions of times, we can obtain a trajectory, a full trajectory followed by our atoms in the system. Of course, we are talking about a Taylor series expansion, so we are considering an infinite sum, which is, in order to be computed, is truncated at some point. The truncation error, that means that the error that we commit in considering only the truncated sum and not the infinite sum, which represents the real quantity, is of the order of delta t to the power of 4. That means that the error is very low if we keep a delta t very low. Let's say that your delta t is 10 to the minus 15 seconds, which is 1 femtoseconds, and which is the order of magnitude of the delta t used in molecular dynamics. You can see that an order smaller than delta t to the power of 4, when it's applied to a time step of 10 to the minus 15 seconds, that means that we are committing a very small error. In the Verlet algorithm, the velocity is not obtained directly from the algorithm itself. And since we need the velocity to calculate quantities such as the kinetic energy from which we can obtain the temperature, we need a way to obtain the velocities for the atoms. One way to obtain the velocity is using this finite difference expression reported here. So basically, the velocity at the time t is obtained as the finite difference between the new position just obtained from the Verlet algorithm at the position time plus delta t minus the position in the previous time step t minus delta t. However, we need to remember that the error associated with this expression is of the order delta t to the power of 2 instead of delta t to the power of 4 that was the error for the integration of the position in the Verlet algorithm. So the Verlet algorithm gives very precise integration of the position of the atoms and less accurate values for their velocities. In Verlet algorithm, one thing that we need to remember is that we need to store one set of velocities and two set of positions for each atom at each time for each atom to obtain the position of the atoms at the new time step. So we need the position of the atom at time t and the position of the atom at the time t minus delta t plus their velocities. We're going to see another method derived from this one, which is better in a sense that it allows to reduce the amount of information stored. We will able to calculate the position of the new atoms at the time t plus delta t using only one set of velocities and one set of position. The Verlet algorithm can be rewritten in a different form, which is called leapfrog algorithm. This algorithm is widely used in molecular dynamics simulation, thanks to the fact that in this case we need to store only one set of positions and one set of velocities. If you remember, in the Verlet algorithm, we need to store to calculate the new position of the atoms at time t plus delta t, the position of the atoms at the old time step t minus delta t, the position of the atoms at the current time step t, and we need the velocities at the current time step v at the time step t. Instead, in the leapfrog algorithm, we only need the velocity calculated now at the 1/2 of the time step in the future, and the position of the atoms at the current time step. With these two quantities, we can obtain the position of the atoms at the new time step t plus delta t. Why this algorithm is called leapfrog? So let's say that we initialize our position of the atoms at the time step t subscript 0. We had to initialize the velocity as well at 1/2 of the time step of the distance with respect the positions. Then along the integration, what we obtain is the velocity at the time step 1/2, the velocity at time step 3 over 2, the velocity at time step 5 over 2, etc. Instead, the atoms they jump over the velocity, and you obtain the positions at the integral time step. So t0, t1, t2, and so on and so forth. That is why it's called leapfrog algorithm. However, this algorithm is completely equivalent to the Verlet algorithm, as you can see from the error here. The error still is of the order for the position is still of the order of delta t to the power of 4, and the velocity that can be calculated here from the velocities at half of the time steps is still of the order delta t to the power of 2. Another version of the Verlet algorithm is called velocity Verlet algorithm. As you can see from the equations reported here, the Verlet algorithm requires to calculate the position of the atoms at the new time step t plus delta t, the position of the atom at the current time step t, the velocity of the atom at the current time step t, and the acceleration that can be calculated from the force. The velocity of the velocity Verlet now is part of the algorithm, is calculated within the algorithm, and the velocity at the new time step t plus delta t is obtained by using the velocity at the current time step and the forces calculated at all time step, at the current time step and at the new time step. The fact that velocity is calculated within the algorithm means that the velocity Verlet algorithm gives both the atomic positions and velocities at the same instant of time with the same accuracy, which is now delta t to the power of 3. Therefore, we usually say that the velocity Verlet algorithm can be considered the most complete form of the Verlet, the class of the Verlet algorithms. Now that we had a look at the different ways with which we can obtain the trajectory followed by the atoms in a simulations, there is only one concept left. How to properly choose the time step for our simulations. Intuitively, we can think that we should choose a time step which is not too short, because we want to be able to sample the largest possible portion of the sample space in a reasonable time. If we need 3 years for a single simulation, that is not good. We want our simulation to finish in days or weeks. However, we cannot take a time step which is too large, because otherwise we will obtain unphysical fluctuation in the energy of the system, and we are not going to correctly sample the fastest degrees of freedoms. If you remember from the previous slides, this is expected because the error in the integration depends on the time step. So larger time steps will give larger errors. How can we decide a good time step for our system? One way to decide a time step is to look at uh, how at the different degrees of freedom of our system, and look in particular the fastest degrees of freedom of our system. What do we mean with fast or slow degrees of freedom? Let's say that we have an aliphatic molecule. We calculate the vibrational stretching of this molecule. And from this, we obtain that the vibrational stretching of this molecule has a period of 10 femtoseconds, more or less. Therefore, if we choose a time step which is larger than this than 10 femtoseconds, what we are doing in our simulation is to not sample correctly these degrees of freedom, because the time step of our integration is larger than degree of freedom. We say that we are not resolving the fastest degrees of freedoms. So a good time step for this kind of simulation is 1 femtoseconds. And that is the general idea. Basically, if we can reduce in some way the 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 motion of these fast degrees of freedom. For example, using constraint dynamics, which freeze the CH bonds, we can increase the time step that we can use in our simulations. For other systems, for example, single atoms in a liquid, we can use even larger time step, because in this case we don't have bonds, fast vibrating bonds. But in general, for all the molecules considered, the time step should be around 1 or even half of femtoseconds. Okay, in the last slide, I will show you a pseudocode for molecular dynamics simulation. A pseudocode is an informal way to describe an algorithm, all the steps of an algorithm, which is not linked to a particular programming language. So basically, in a pseudocode, you list the operation that you want to perform to do the task that you need to do. So in this case, a typical molecular dynamics simulations code will look like the pseudocode presented here. Of course, it will depend from the specific programming languages. There will be other models included. So, but the structure, the backbone of any MD code is going to be like this. So we have an initialization of a reading of the parameters that specify the system, initialization of the position and velocities of the atoms. Then for each time step, for the number of time step that we want to perform for each time step, we calculate the force, we integrate the Gratian motion, and then we calculate whatever properties we are interested in, usually averages of energies, kinetic energy, potential energy, and so on. Then we repeat calculation of the force, integration, calculation of the averages, etc., etc.